Bismillahirrahmanirrahim. This is Pakistan International School Taif and class second year grade 12. We are continuing chapter number 14, D-block elements, and I think the lecture number is 22. And last time we done the potassium permanganate as a oxidizing agent, and also here we few examples we done potassium permanganate acts as oxidizing agent in the titration as well as in the organic compounds. So I give you example for the organic compound, and here this potassium permanganate act as oxidizing agent in titration. So these are the highly colored compounds. Potassium permanganate and potassium dichromate are the highly colored compounds. So that's why they are going to be oxidized other substances and reduce themselves. And these titrations are called redox titrations. In these redox titrations, so these highly colored compounds, there are no indicators used from the outside. They act as self-indicators. So there is equations given: potassium permanganate, manganate 7 oxidation number, used to find the concentration of all sorts of reducing agents. Means potassium permanganate oxidizing agent and other are reducing agents, and they are going to be oxidized. And we use acid in the presence of acid, acidified potassium permanganate. So students, the equation is given here. I am going to write, see this one, potassium permanganate, sulfuric acid dilute sulfuric acid, about half test tube you have to add, and you will get potassium sulfate in aqueous solution, manganese sulfate in aqueous solution, and plus 3 water molecules liquid, and there 5 nascent oxygen atoms. And written for the potassium permanganate, same that potassium permanganate K2Cr2O7 with the dilute sulfuric acid also gives the nascent oxygen, and this nascent oxygen is going to oxidize a reducing agent. So this is the main equation when you write the oxidizing nature of potassium dichromate or potassium permanganate. This is the main equation, how the nascent oxygen is going to be produced and how it is going to be oxidized, the reducing agent. So equation is given here. It is going to oxidize ferrous sulfate. Which is a very light green compound, and sulfuric acid, we have to dilute it, we have to put some acid, acidified the sulfuric acid, and the same this nascent oxygen is going to be used to oxidize this ferrous sulfate, and this ferrous sulfate changes into ferric sulfate. So ferric, the valency of iron is 3 here. This is the ferric sulfate and plus water. And because you are seeing that there are five oxygen atoms, so whole this equation is multiplied by 5. So you can see here potassium permanganate, I told you positive sign, positive 7 for the manganese, and here positive 2 for the manganese. There is a reduction. The substance which reduces itself is called oxidizing agent, and nascent oxygen is going to be produced in this process. So this is a very light green ferrous sulfate aqueous. So the oxidation number of iron here is a positive 2, and here our iron is a positive 3. So there is a oxidation, and this oxygen is going to be oxidized and consumed in this chemical reaction. So when you are going to add this oxygen 5, and this oxygen is going to be cancelled out. So you have now overall reaction, potassium permanganate, positive 7 oxidation state on manganese, plus 2 ferrous sulfate, oxidation of our iron is positive 2, sulfuric acid 3, and the 5, 8 dilute sulfuric acid, oxygen is consumed here, and potassium sulfate, low change in oxidation number, manganese sulfate, yes, oxidation number is going to be changed, reduction taking place, and 5 water and 3, 8 water molecules. So students, there is a reduction, and also the main is ferric sulfate, and oxidation of iron is positive 3. So 7 changes into positive 2, there is a reduction in manganese, and positive 2 changes into positive 3, oxidation in the iron. So this titration is used in the laboratory, we call redox titration. And there is no indicator is used. Potassium permanganate, highly colored compound, itself acts as an indicator. This is the one example which is given here. Write down in your book. Also write in your copy. Must you copy it? This one. Do it. Second example. In second example, the students, you are seeing oxalic acid, ethanoic acid, oxalic acid into carbon dioxide gas. The reaction has to be done hot, means when we are running in the laboratory, 60 degrees Celsius. You have to give 60 degrees Celsius, I will explain. Same equation, 2 moles of potassium permanganate, 2 moles of potassium permanganate, and plus 3 moles of dilute sulfuric acid to give potassium sulfate, same equation which we wrote before, and also manganese sulfate, plus 3 water molecules and 5 nascent oxygen. This is a previous equation, same 100% same. The oxalic acid, H2C2O4. Actually, structure is COOH and COO. This is the oxalic acid, ethanoic acid. Ethanoic acid or oxalic acid, H2C2O4 oxalic acid. Nascent oxygen is going to be oxidized and changes into carbon dioxide gas, and you have to heat up to the degree centigrade to evolve this carbon dioxide gas very well. 2 moles of water and whole multiplied by 5. The whole equation is multiplied by 5. Okay, now if you are going to add this, there is a 2 moles of potassium permanganate and 5 multiplier moles, so plus 5 oxalic acid moles, H2C2O4, oxygen 5 cancelled out, and 3 sulfuric acid, no sulfuric acid is there, 3 moles of sulfuric acid on the reactant side. On product side, you are seeing potassium sulfate and 2 moles of manganese sulfate plus 2 moles of carbon dioxide gas, and there are 3 moles of water. No, oxalic acid are 5 moles, and this carbon dioxide gas 2 multiplied by 5, 10. There are 10 moles of carbon dioxide gas because you are seeing 5 multiplied by 2, and water 5 multiplied by 10 and 313. So wrong. So here there is oxidation, and in hot conditions means you have to maintain temperature of the solution by a thermometer is 60 degrees centigrade, not more than 60 hot. You have to use a solution which is given the condition in your book. So this is number 2nd equation. Write down this one. Write down written. So this is about the titration of oxalic acid. How potassium permanganate acts as oxidizing agent, and oxalic acid is going to be reduced itself. 3rd example. Sulfite ions. Same equation I am going to write 2 moles of potassium permanganate plus 3 moles of sulfuric acid, dilute 1 mole of potassium sulfate and 2 moles of manganese sulfate and 3 moles of water and 5 moles of nascent oxygen. So sulfite changes into sulfate. Sulfite means sodium sulfite. This is a sodium sulfite, by nascent oxygen is going to be oxidized and it changes into sodium sulfate, and there is a multiplier by 5. Sodium sulfate is going to be formed. So how there is oxidation and reduction, it is the same. Manganese positive 7 and manganese positive 2, and there is a reduction in manganese and giving 5 atoms of oxygen. This oxygen is a -2 multiplied by 3, -6. And this is a +1 multiplied by 2, +2. So it means that it should be +4. The oxidation number of sulfur is a +4 here. So in the sodium sulfate, oxygen is a -2 multiplied by 4, -8. Sodium alkylated, +1 multiplied by 2, +2. The sulfur is +6. So this means sulfur is going to be oxidized. Sulfur is going to be oxidized, and there is a oxidation. When you add these two reactions, 2 moles of potassium permanganate and 3 moles of sulfuric acid, 5 moles of sodium sulfite, oxygen cancelled, 5 cancelled out. Product side, 1 mole of potassium sulfate, 2 moles of manganese sulfate, and 3 moles of water, and 5 moles of sodium sulfate. This is the net reaction, overall reaction. And third example we done for the oxidizing nature of potassium permanganate, how it oxidizes. So we done 3 examples. Number 1 example, for the ferrous iron 2 sulfate is going to be oxidized. In the second example we done for oxalic acid, and this is the third example we done for the sodium sulfite changes into sodium sulfate. And the oxidation number of the sulfite is here, sulfur is +4, and it's going to be changed into +6. There is the oxidation. Now here, reaction of potassium permanganate to potassium ferrocyanide. We done the complexes. Potassium hexacyanoferrate. Potassium hexacyanoferrate 2 changes into potassium ferricyanide. Means this is the structure is wrong in your book. Potassium hexacyanoferrate 3. 2 changes into 3, so I am going to omit this one. Oxidation of potassium ferrocyanide to potassium ferricyanide. Same reaction. So this is reaction is given on the next page, page number 82. First time reaction. Potassium permanganate +7 plus 3 sulfuric acid to give potassium sulfate, manganese sulfate plus 3 water molecules, 5 nascent oxygen. So this is the 5 multiplied because 5 oxygens are there. So this one is a potassium 4 square bracket, iron, oxidation number is +2, cyanide ligand. There are 6 cyanide ligands. Yes, I'll explain. This is the nascent oxygen, and there is a water. You see, and also changes into potassium 3. Yes, now there the structure is correct. In the previous page, the structure was wrong. 3 cyanide 6 bracket over 2 moles of potassium hydroxide. Okay. So this one is a potassium permanganate, means manganese dioxide. Potassium sulfate, manganese sulfate, positive 2. So here is oxidation of iron positive 2, and the name is, I told you according to the nomenclature, potassium hexacyanoferrate 2. Oxidation of iron is 2, and this one is a potassium hexacyanoferrate 3. The potassium ferricyanide is a potassium ferrocyanide. So if you add, there is oxidation in the iron. Iron is going to be oxidized, and potassium permanganate and sulfuric acid free moles of sulfuric acid, and this is 5 is plus 10 potassium hexacyanoferrate 2. Oxygen are going to be cancelled out, and this one water molecule and 3 remain behind. On the product side, potassium sulfate, manganese sulfate, 2 water molecules, and also you have because there are how many 2 and 5 10, and this 5 is multiplied also here, so there are also 10. There are 10 also. Potassium hexacyanoferrate 3 and 5 multiplied by 2, there are 10 potassium hydroxide. Yes. So this is the oxidation of potassium hexacyanoferrate 2 to potassium hexacyanoferrate 3. You are calling potassium ferricyanide. So these are the examples of the oxidizing nature of potassium permanganate in titration. Now, while doing the titration, the potassium permanganate solution always go into the burette because it's a highly colored compound, acts as oxidizing agent and also self-indicator. And other solution are flows in the by using sulfuric acid, we are going to acidify them. As the potassium permanganate solution is run into flows, they become colorless. The end point first faint traces of permanent pink color, and the solution showing there is excess potassium permanganate cyanide ions. One thing I will tell you, then I am going to stop. Potassium permanganate is not a primary standard. Potassium dichromate is a primary standard. Primary standards means when you are going to make the solution, they are stable. They are not going to be oxidized. Light is not going to affect on those solutions. But if you put potassium permanganate in the transparent glass, transparent bottle in the laboratory, so light is going to be affected and change oxidation number. So you are not going to use again for tomorrow. You have to prepare again. So it is unstable. So this is not a primary standard, which is unstable, showing instability. So this is the difference between primary standard solution and other one. Potassium dichromate is a primary standard, but potassium dipermanganate is not a primary standard. So students, we are going to finish here, and inshallah in the second lecture we start iron. This is also very important transition matter. Go through this book also, see exercise questions, also see the board papers, write each and everything from the board and in your copy. Thank you very much.